All right, hi everyone. On behalf of the entire ACT collaboration, I want to welcome you to our second webinar, which will focus on the ACT DR4 data products. And this set of data products includes temperature and polarization maps that cover almost half the sky at high resolution that we hope many of you will find very useful for whatever projects you can conceive, but also involves lensing maps, component separated maps, spectra, some catalogs and likelihoods. And what we really want to do is make sure that we publicize what we've put out there and also help you and the broader community understand how to work with our data and what tools we've provided to help you along. So the format of this is that we're going to start off and have Simone give an overview of the data products. Matt will come in after that and give an overview of Pixel, which is the software tool we have for working with our maps, which are not in the Healpix format. So we've hopefully made that quite easy for you to work with this tool. And then Maya and Zach will come in and provide an overview of the Jupyter IPython notebooks that we've supplied that largely Maya and Zach wrote to help you get started with the data and carry out some of the simple analyses that we might think that you want to work with. And I'll just say as an advertisement that following this, in the next few months, we plan to hold a longer format school to give people more hands-on exercise with all of our tools and data products. And so keep your eyes out for that. And if you have questions about that or interest in it, let us know. Okay, with that, I'll hand it over to Simone, who will give you an overview of the DR4 data products.
Yes, thanks, Jeff. Hello, everyone. As Jeff mentioned, we are presenting on behalf of the entire ACT collaboration. So here I just want to show you a picture of all the scientists, graduate students, postdocs, and faculties that really work hard on ACT, from building it all the way to analyzing the data. And so what we're presenting today and all the data we were able to release is really thanks to the work of everyone and not just us here presenting. And so, given the focus of this webinar, let me tell you where you can find the data products and what kind of data products you'll be able to access from ACT. So currently, the data is hosted on the NASA LAMBDA website. So it's fully public, and as you can see from the NASA LAMBDA website front page, the data release from ACT is here now. And so you'll be able to download several data products. Those are roughly 0.5 terabytes of data that we released. So what do we have? So the lowest level product that we released to the public are multi-frequency maps. Those come separated by season. We observe in several seasons, and here this DR4 data release covers from 2013 through 2016. So those maps are divided by season. They're also divided by patch. And here you can see sky coverage from ACT with the different patches and their names that we cover, and where the advanced ACT patch roughly covers 40% of the sky. We also divided by optical array, what we call PA1, PA2, and PA3 polarized arrays. And of course, there are single frequency maps. Each map comes in a bundle of different products that includes inverse variance maps. That's the inverse variance number in each pixel that helps you defining the statistical weight of each pixel. What we call cross-linking maps, which you can think about it as IQ and U Stokes parameter maps that encode information about the scan strategy. That's quite useful for such a large coverage of the sky because the noise properties are varied across the sky. And so you would like to know how cross-linking is varying as function of declination, for example. And then the actual data is provided into two subsets. One is the sky maps that have been point source subtracted. We resolved a lot of point sources, and it's useful to have those removed, especially if you're performing FFTs. And then those sources are provided in a separate map, and you can simply add these two together to get the observed milliliter sky at one of these frequencies. So that's the lowest data product you can find. It was described in the Yale et al. Paper that just came out. But from this information, we derive some other maps. We derive what we call the coad maps. That's optimal coaddition of all the different data sets, including ACT DR4 or ACT plus Planck. And here by Planck, we include the 100 and 143 gigahertz channels. So those are, again, our single frequency. They're all co-added, so you will be losing information on the arrays and seasons, but those are probably the easiest maps to work with. For these maps, we do not provide data splits at the moment. We have component-separated maps. Multi-frequency information is very important, and the fact that we can use ACT and Planck to work together, that allows us to extract single components. And so we have CMB plus KSZ maps, so basically the black body component over the D56 and Boston region, as well as TSZ or Compton Y maps, again in this region. And both of these maps are provided with and without CIB the projections. We can also reconstruct lensing. And so we have two lensing maps, again, over the D56 region and the Boston region that give you the lensing kappa field over the sky. And those have been reconstructing, the baseline version of these maps was reconstructed by using ACT and Planck component separated maps with TSZ projected. So those are the map-based products that we release. We have some auxiliary products that we do need to release in order to fully describe the data that we have. That includes masks, point sources, if you would like to mask point sources and extended sources like you would do for a power spectrum analysis. We release footprint regions, so you'll be able to know exactly which regions we have taken for the power spectrum. Oops, sorry about that. We have lensing masks and masks for the component separation. We also have several window functions that includes beams, leakage beams, transfer function from the map maker, and beams for the component separated maps. Those are, here you can see all the different papers that have described these products. Using these maps and all these ancillary products, we can derive spectra. That's one of the statistics we do. And here we have the usual CMB spectra. We have both a multi-frequency version where the spectra are taken by combining the different frequencies or looking at only the 98 and 150. We have CMB only, where we marginalize over foregrounds. So if you're interested in only the cosmological part, those are the power spectra you can use. We also have birefringent power spectra, so the power spectra from reconstructing the signal from the cosmic birefringents, as well as the lens spectra in a multi-frequency format. With this spectra, you can define different likelihoods to do cosmology. So we have a multi-frequency likelihood, and this is used to sample over both CMB and foreground parameters. But again, if you're not interested in foreground parameters and you would like to combine also with other experiments, one preferred solution is to use the CMB only likelihood based on the CMB only spectra. Can be used to sample over CMB parameters, and that's what we use for our baseline results in combination also with WMAP and Planck. And we have both a Python and a Fortran implementation of this likelihood. And we also have the likelihood that was used to extract parameter from the lens spectra. We appreciated sometimes running chains and extracting cosmology from these data sets is time consuming and it requires computation. So we also put the sort of the highest level product that we put out are what we call cosmological results, which for the likelihoods are basically all the chains from our parameter runs. So we put out chains from the ACT only runs, ACT combined with WMAP, our baseline cosmology, and ACT plus Planck. We also have chains from the lensing likelihood. Again, this is multi-frequency, so you also have foreground parameters. And for the lensing parameters, we'd also put out the covariance and the parameter shifts between the normal and the lensed spectra, parameters that you would estimate from the normal and the lens spectra. So as I mentioned, this is a very quick overview. It's a lot of product that we put out there, roughly half a terabyte. And we also have associated simulations that will be available in NERSC shortly. As a matter of fact, both the products and the simulations will be available in NERSC. If you're a NERSC user, you'll be able to find them on the community file system, or we are also trying to make it accessible via web, so you will not need to have a NERSC account. I want to also mention that there will be a paper coming out in the next month or so, led by Maya and Zach as an explanatory support that will tell you exactly how these, what these data products are and how you should be using that. And in general, if you have any question while downloading and using our data, we do have a help desk email address that you can email us to, and the person responsible for that product will try to get back to you as fast as possible. And so now I'm gonna hand it over to Matt Maravachero, who's gonna be talking about Pixel, the library we use to handle the maps.
All right, thanks, Simone. So I'm going to be talking about Pixel, which is a software for manipulating maps in rectangular pixelization. The reason I'm talking about this is because many of you might be familiar with Healpix, which is the format that WMAP and Planck, the WMAP and Planck CMB experiments put their maps out in. Our maps are out in a specific projection of a rectangular pixelization. There's multiple reasons for this. We want to make our maps available to the astronomical community as well, so that's one of them. So just to give you a little bit of background on what, how you can use these maps and the software you can work with to load these maps with. This will be a brief introduction into a longer tutorial that you can find on the internet that I'll point you to. So what Pixel can do is manipulate maps, as I mentioned, in rectangular pixelization, but it can also do many additional things like calculating Fourier transforms, spherical harmonic transforms, reprojecting and interpolating between different systems, simulating maps, including simulating lensing of these maps and simulating point sources. What it cannot do are things like, proper cosmological precision pseudospectra, the kind that you would need to calculate power spectra in the papers that we just released. There are other software for that. It cannot also do things like lensing reconstruction and cluster source finding. But it does form the backbone software that many of these software on the right side use. First, I want to start out by contrasting with Healpix. So this is, as I mentioned, this is the pixelization that most CMB maps from satellite experiments have been put out in. So what you can think of Healpix as a way of mapping dividing the entire sky into equal area divisions, and then those regions are then mapped to a one-dimensional array in memory. You can think of rectangular pixelization as doing the same thing, but mapping it to a two-dimensional array. So one advantage of this is that you can load these as NumPy arrays in Python, for example, and then slice and work with them. There's many different ways of doing that mapping, and so cylindrical is one of the cylindrical projections is one of the ways you can do it. We'll see that in a bit. So while Healpix maps can be analyzed with a Python package like HealPy, Pixel is basically a Python package that lets you analyze rectangular pixelation maps. And I should note that the lead developer, the person who's contributed the most code to this, is Sigurd Næss at Flatiron Institute. So the way you want to think about using rectangular pixelation maps, and if you're an astronomer, you're probably already familiar with this, is the world coordinate system. So that's this is a system that lets you translate between pixel coordinates and sky coordinates. It essentially defines a set of key value pairs in a FITS file header. And those key value pairs give you a unique mapping from a pixel coordinate in a 2D grid to a sky coordinate. And once you have that mapping in place in your software, and that gives you all of the info you need to do any kind of analysis or physical inference from those maps. I want to spend a minute to address a misconception. So once you get a map in rectangular pixelization, that does not mean that it is quote unquote flat sky. So both Healpix and rectangular pixelization have they have a scheme that's information preserving up to pixel averaging for mapping sky coordinates to pixel coordinates. The fact that rectangular pixelization lays it out on a 2D grid does not make it a flat sky representation. What makes your analysis a flat sky representation, or makes you have a flat sky approximation, is how you, for example, calculate a harmonic transform with it. If you use an FFT or fast Fourier transform to calculate a harmonic transform of your map, then you're making a flat sky approximation. But if you have software that lets you calculate a spherical harmonic transform on a 2D grid, which is entirely possible with Pixel because it uses the libsharp library, then there is no flat sky approximation. So at least in terms of harmonic transforms, there's the fact that you have a rectangular pixelization does not mean you're in a flat sky system. And so I want to highlight that Pixel lets you do spherical harmonic transforms with the maps. In fact, that's how the partial spectra analysis in our recent set of papers was done. Once you specify that you have rectangular pixelization, you can specialize to specific projections. And the projection that we've used in ACT is a cylindrical projection. One thing I do want to point out is that previous ACT maps had a slightly different projection. So they used a cylindrical equal area projection. The advantage of this is that every pixel has the same area, so that makes things a little bit simpler. But in DR4 and moving onward, we use a slightly different projection, cylindrical projection called plate carry, which is a very simple linear transformation between the pixel coordinates and the longitude and latitude. The main advantage of this is that spherical harmonic transform, it's easy to calculate spherical harmonic transform for these because they already exist in libsharp. The point, though, is that Pixel as a software kind of abstracts away these projections, so you don't have to think about it. When you load a map, you don't have to think about whether it's in CEA, the old ACT format, or CAR, the new DR4 normal format, or the ZEA format from SPT, for example. You're able to load any of these maps with the same software and use the same commands on them to analyze these maps. So I'll just sketch an outline for the tutorial that you can find linked to in these slides. If you use the video tutorial, it'll go through an IPython notebook that shows you how to download an ACT map and a cluster catalog and a Planck map. And you can inspect the map, you can plot the map in various ways, you can inspect point sources, you can filter the map, reproject it, calculate spherical harmonics, etc. A lot of these things will be covered in the notebooks that Maya and Zach will talk about in a bit. So you can see them in action there as well. The installation procedure is very simple. It's available on the Python package index, and you can install it with precompiled binaries. And you can find a tutorial notebook here and a YouTube video tutorial as well. With that, I'll hand it over to Maya and Zach.
Great, thanks, Matt. As has already been mentioned, Maya and I have created a set of IPython notebooks to accompany the DR4 data release. And you know, the goals of these notebooks are really to maximize accessibility and utility to the cosmology community, sort of in the interest of becoming a go-to data set. So these notebooks represent a subsample of some of the analyses that we perform in DR4. And in particular, we will present a further subsample of these notebooks to you today, just in the interest of time. So take it away, Maya.
So as Zach mentioned, one of the things we're aiming for here is to make sure that the notebooks themselves and the data release in general is accessible. And so with that in mind, we have two methods you can use to get set up with these notebooks and run them yourself. So we'll look at the notebooks themselves in a minute, but so you have an idea of how they actually work, you can go with the local installation, which is basically just involves installing the various CMB analysis tools, such as Pixel, which Matt mentioned, and then HealPy, PyAct-like, and a range of other products. And then you would clone the repository and download the necessary data. This can work well if you already have some of these packages installed, or if you're kind of comfortable doing this yourself. If you would prefer not to go through installing all of these packages, we also have a Docker container, which comes with all of these analysis tools already installed in the container, and so might be a sort of simpler and more straightforward way to get set up with these. And then you would also have to download the data. So I will say that a caveat here is that, as has been mentioned by Simone earlier, there is a lot of data here, and we do use quite a lot of data in the notebooks, and so this can be a little bit time consuming. So we actually have scripts that you can run, and the data will just download in the background while you're doing something else. You could also choose to just download the data for a subset of the notebooks if you prefer to do that. But instructions on how to do this, as well as how to access the notebooks themselves, can all be found on the GitHub linked here. We also have a help desk specifically for these notebooks. So Simone mentioned a help desk that was for the actual products. This is one specifically for how to get set up with the notebooks and how to use these notebooks. So the Google group email address can be found on our GitHub, or it's here if that's easier for you. So into the actual notebooks themselves, we have 12 notebooks that we've included here, and I'll give you a brief overview of them. The first couple are kind of introductions to the release itself, and Pixel. So this will complement the tutorial that Matt mentioned. And then we spend some time looking at the different data products. So we have a notebook specifically for lensing maps or specifically for the component separated maps. We also have a couple notebooks looking at how to generate power spectra, both using Pixel and then also using a code called NARWrapper. And then we have a notebook on noise simulations, one on polarization. We have a notebook using the ACT likelihood code specifically, and then a notebook that's been added recently that uses the delensing parameters from the recent Han et al. Paper. So in the interest of time, we won't be talking about all of these. We'll instead just be discussing these 4 notebooks, and I'll look at notebook 4 and 5, and then Zach will come back and tell you a little bit about 9 and 11. If you have questions about other notebooks, you could definitely ask them here, or you can email our help desk for more questions. So before we actually look at the notebooks, just to give you an overview of what notebook 4 is doing, this notebook focuses on looking at point sources. So we use a catalog of point sources from a previous ACT data release to go in and look at these, they're normally galaxy clusters in our maps, and show you how to cut out small patches of maps, look at these small stamps, and then also how to look at radial profiles of these sources, if you're interested in doing that. I will also be looking at notebook 5, which uses the lensing maps. So for this notebook, we'll show you how to read in a lensing map, and then also how to generate a galaxy density map, which you can then cross-correlate with the lensing map. So this is great if you're interested in cross-correlations with probes other than a CMB map. It's a really good place to look for an example of that. And then also if you're interested in working with the lensing maps, there is quite a bit of detail around how the lensing maps really work. So now I'm going to jump over to the actual notebooks so you can look at what you'll see when you open the notebooks yourself. Okay, so here is one of the notebooks. I'll scroll up to the top. This is notebook 4. So all of the notebooks have a kind of similar setup in that you'll see a brief introduction, a table that has the dependencies for the notebook, as well as the data products you're using in this particular notebook. And then you'll see the table of contents. You'll see us set up the notebooks and then read in the maps. So in this case, we're reading in 2 here, and this process is described in much more detail in notebook 2. So if you need that kind of background, it's there. And then we're going to read in a cluster catalog. So in this case, we're using one from DR4. So that's an older cluster catalog, but you could definitely go in and replace this with your own catalog if you wanted to. And once you have that catalog read in, you can use it to look at a point source in the map. And so this is a pretty simple approach where we're just going to basically take the location of a point source and cut out a box around it and look at that. But as Matt has mentioned, we're using this rectangular pixelization for these. And so one of the things that you may want to do with this is reproject it so that you're at a map that's centered on the location of the point source. And we're actually going to reproject to a map that's tangential to the location of the point source. So we show you how to do that. We also have some more explanation about how this works. And throughout the notebooks, we try to include quite a bit of text so you understand how things are working. But Pixel makes this reprojection really easy. It's a sort of one-line command here, this reproject command, and you get a new map centered on the location of the point source. So the next thing that we look at in this particular notebook is how you can stack on these. So if you have an entire catalog, what you might be interested in is the sort of average signal from a cluster of from that catalog in your map. So we show you how to reproject all of these thumbnails, stack them on top of each other, and then you can look at the average signal of a cluster in our map. And again, you could do this with a different catalog if you wanted. You could look at individual galaxies, see if you can see a signal from that, or if you have a different cluster catalog you're interested in using, you could do it with different maps. As Simona mentioned, we have a range of them. Definitely go ahead and plug in a different map here if you wanted to. I'm gonna jump forward to the next notebook in the interest of time, but to give you an idea, this notebook also then goes on to look at the radial profiles of this. So if you're interested in that kind of code, then definitely come back to this notebook later and look at that. So switching gears a little bit, notebook 5 is pretty different because instead of looking at these sort of small scale point sources, we're now going to be looking at an entire lensing map, and we're going to be looking at how you can do a cross correlation using these lensing maps. So we again have an introduction, we go over the data products you'd need for this notebook, have the table of contents, we initialize the notebook, and then we read it in a lensing map. So this is a view of an overall lensing map that we have. And this is the same lensing map, but just zoomed in, cutting out a smaller patch to show you a little bit of the detail that's going on there. And these tools of how to look at the maps are described in more detail in a previous notebook as well, but here we just reuse these commands up above. So once you have the lensing map, what we want to do is cross-correlate with a galaxy map here. And so we're actually going to do this using the Healpix or Healpix convention, because a lot of people are familiar with that, and in later notebooks we'll show you how to do a similar thing, but using pixel instead. So we can start off by reprojecting that lensing map into the Healpix framework, and so that's what you're seeing here. This is still the lensing map, but now we're just using the more wide view projection from Healpix. And this reprojection is again pretty straightforward using pixel, but we also have a notebook that focuses on this kind of reprojection, so you can look at how this really works. And then once you have that, you want to make an overdensity map. So in this case, we're using C-mass galaxies, but you could use a different set of galaxies if you wanted to. And we use that to create this galaxy map here, which is again in the Healpix projection. And so once you have these two Healpix maps, you can go in and cross-correlate them. And so in this case, because we're using the Healpix setup, we're going to use spherical harmonic transforms. And one of the things you have to think about in general when you're doing cross correlations is how you're applying window functions. And so before we go and actually cross correlate, no need to read this all, but you can see there's quite a bit of text around how the window functions work and how you should go about thinking about using these lensing maps. So one of the things we're trying to do here is make sure that we're not blindly giving you code that you follow along, but that you have the sort of understanding and the tools to adapt this to your own uses. And so we're explaining how the window functions are used here and how to account for them in the specific case of these lensing maps. So once you have the lensing maps and the sort of understanding of the window functions, we go through and actually apply some different windows and account for those window functions. And then we go and cross-correlate. Again, here we're going to be using Healpix cross-correlate, but we do have examples later on of how to do this using pixel. And so we use Anafast, which is a pretty common tool from Healpix that shows you how to do this cross-correlation. And then once you have that, you can plot your cross-correlation pretty easily using straight up matplotlib. And this notebook is a great place to look if you're interested in lensing maps, but also in general, if you want to know how to use other data products with these CMB maps. It's a great place to look for that, for how to set up those galaxy density maps or how to convert these maps to Healpix to do cross correlations using Anafast. So with this, I'm going to hand back to Zach, who's going to talk a little bit more about a couple of the other notebooks that we have. And if you have questions, feel free to ask them in the end, and we'll get to you.
Great, thanks, Maya. Let me just share my screen. Okay, cool. So as Maya mentioned, one of the notebooks that I'll be discussing is how we generate our noise simulations according to the prescription that's outlined in our Choi et al. Paper. One of the great things about this notebook is that it deals with the data at sort of its lowest most fundamental level, as Simone discussed. So we use the split data maps that are released per season, per frequency, per array, per observation paths. So we get to again work with the data at a low level. So we'll talk about reading in this data, how we manipulate the data using pixel to look at it in Fourier space. and then how we massage this data in order to emerge with the actual realizations of our noise in map space. And so let's take a look at this notebook real quick. So before I actually look at this notebook, I just wanted to give a brief mention. So as Maya talked about in terms of the installation of this repository, there are sort of two options. There's the Docker installation and there's a local installation. I have chosen to go the local installation route. And in that case, we just had to make one change in the first notebook, which is explicitly specifying the path to all the data that we download and work with. And once we do that here, this change will propagate into all the other notebooks. Great. So actually moving into our noise simulations. So as Maya discussed, we outlined the actual data products from DR4 that we need to make this notebook work. So we see our split source-free maps. We see one of the window functions, or excuse me, window maps that Simone mentioned, as well as the inverse variance maps that accompany these split maps. And then finally, one of the simulation products that Simone mentioned will be released on NERSC. Great. So one of the first things that we do in this notebook is we just read in our raw data and take a look. So for the particular patch array and frequency and season that we examine in this notebook, we load in our data. And again, this data is a quote unquote split map, which basically means it's a map produced from a set of non-overlapping sections of the time order data. So it's multiple independent realizations of our noise, and from this is how we will produce our estimates in our noise simulation. So here we see one of those splits, as well as our apodization window mask, which is discussed in Choi et al. Moving along, we also read in the inverse variance maps that Simone discussed. So these maps give the small scale RMS noise magnitude estimate in the sky. Again, on the per season, per array, per frequency, per patch basis. And obviously this will play a key role in our noise simulations, but here we show that estimate of the RMS error in our patch. And so we can see that the region corresponding to generally low area or low error lines up in area with our apodization window, which makes sense. So moving along, what we do is we subtract all of our split maps, or subtract from our split maps the coaddition of all those splits. So this removes all of the signal in map space and leaves us with an estimate of our noise. And when we look at that noise, we see, again, this is Stokes I, Q, and U. We see quite a lot of large scale or low L features, and these, of course, generally correspond to atmospheric modes. We can then use Pixel. Let me just scroll down here. We can use one-line operations within Pixel to take the Fourier transform of these realizations of the noise, and we can examine the 2D power spectra of the noise. And what we see is sort of interesting anisotropy in this 2D power spectrum, which will be some complicated function of the scanning strategy that Simone talked about earlier. And sort of the game here is to attempt to remove some degrees of freedom from these auto and cross spectra, and emerge with an estimate of our full noise covariance matrix and map space from which we will actually draw our simulations. Just in the interest of time, I'll kind of skip some of the most technical bits. We emerge out of this process with what is essentially a smooth version of this 2D or this set of 2D cross and auto spectra of our noise. And this is what we actually use to generate our noise simulations. And so we can load from disk one of the data products that will be released on NERSC, the actual covariance matrix itself. It's a very simple operation from there to draw samples from the distribution that is described by this covariance matrix. And so that's what we show here. Pixel, again, is providing all of our basic functionality in terms of all of the linear algebra, which is fantastic. And from this data product on disk, we emerge with an actual sample in map space from this full noise covariance matrix. So that does it for noise simulations. And the second notebook that I'll talk about now is working with the ACT likelihood. And of course, this lives on the opposite spectrum. So rather than opposite end of the spectrum, so rather than working with the data at a low sort of fundamental level, we get to work with the data at a very high level. And so this notebook performs a few functions. So we get to examine our best fit spectra. We get to examine how those best fit spectra perform statistically against our data and examine the likelihood of those spectra. And then finally, we work with some of our MCMC chains. So let's move over to that notebook. Great. So first things first, we use the PyAct-like repository, and this PyAct-like repository is packaged on LAMBDA as one of those ActPol products that Simone mentioned in his presentation. And so you can actually download this repository in full from LAMBDA and follow along. So the first thing we do is instantiate a PyAct-like ACT power spectrum data object, which will perform basically all of our core functionality here. So for instance, when we install this repository off of LAMBDA, we get for free our set of best fit spectra. And so we can actually plot those spectra and take a look. So here we see the TT and EE spectra. And of course, we can kick it up a notch, and we can start to evaluate the likelihood of these spectra against their actual data. And so again, the PyAct-like repository that we install enables us to do this quite easily. It's just a one-line call to that raw data that we loaded, and we get a chi-squared, which reflects the full covariance of all of our binned power. And not only that, we actually pre-package the data, the raw data that comes out of our power spectrum code, so we can plot that against our best fit spectra. And we see, of course, here a good fit to the data. And we can look at the difference between our best fit spectrum and the data itself and examine the residuals, and we see an even scatter across multiple. And of course, we can use this to alternatively come up with sort of a diagonal estimate of our chi-squared, so not using the full PyAct-like covariance, but just looking at the raw errors that we see here in the residual. And we see, again, a sort of a good statistical match between our observed chi-squared and the number of data points that we have. Of course, we can do this in polarization as well. The TE and EE data come along for the ride in this PyAct-like object that we loaded in earlier. And we can look at those cross and auto spectra here. And again, we see a good fit for our best fit spectra against the data points. And we can just repeat the process that we did for TT. So we see a nice even scatter in the residuals across multiple. And then finally, we can examine the chi-squared in polarization as well. One of the great things about this framework is that it allows us to test essentially any cosmological model, even though it's not described by LAMBDA CDM. So you can throw in any sort of fiducial spectrum that you want and compare it to our data and examine the statistical properties. So just for fun, we come up with a model that uses our best fit H0 estimate and a not flat universe, which we expect to give a poor fit to the data, but you know, we generate that power spectrum and plot it against the data points. And of course, we see that now our spectra are quite out of phase. But nevertheless, if we wanted, we can look at the likelihood of such a spectrum against our data, again, using the same one-line call. And of course, we see the chi-squared is quite high, but nevertheless, you get the idea. Any cosmological model, including those not parameterized by LAMBDA CDM, can be evaluated statistically here. And then finally, we look at one of our MCMC chains, which will give the full joint distribution of all of our cosmological parameters. So first, we take a look at the parameter space that we're dealing with, which is highly or high dimensional, of course. But we show you how you can extract interesting parameters from this joint distribution. For instance, look at the marginalized distribution of just the Hubble constant, or in 2D, the Hubble constant against the matter fraction. And then finally, you know, smooth versions of these marginalized distributions as well. So hopefully this notebook will be quite useful and relevant for the theoretical community. And that's all for us.
Great, thanks everyone. So at this point, we'll open it up for questions. And I just want to give everyone some logistics of that. At the bottom of Zoom, you'll find a Q&A button. And if you hit that, you can then ask your questions. So far, we have one, but if you have others, please ask, and that's the way that we'll route those to the right person to answer. So the first question we have comes from Ira Wolfson. And it's a question for Maya, which is which I'll paraphrase as where can I find the link to the data downloads and the notebooks? And Maya, why don't you answer that?
So Joe Dunkley has put a link to the actual notebooks in the chat, so you can see it there. But if you're later trying to find it, one of the easiest ways is to Google LAMBDA and ACT, and that'll take you to the LAMBDA ACT website. And from there, where you see our list of data products, there's also a link to the notebooks on that main page. And that's also where all of the various data products are linked. For now, they will be added to NERSC at some point very soon. But for now, all of the data products that you would want are going to be on that main website for LAMBDA.
Great, thank you, Maya. Okay, so the next question is for Simone, and it comes from Tal Abadi, and I apologize if I'm mispronouncing your last name. And the question is, hi, how does the ACT likelihood integrate with MCMC code such as Cobaya or Monty Python?
Sure. So let me just say, for the basic cosmological results that we presented in the papers, we used CosmMC. So the Fortran likelihood was interpreted with CosmMC. And in the READMEs, you'll be able to find which version of CosmMC was used and what modifications were adopted. The Python version is exactly to be used for things like Cobaya and Monty Python. So you should be able to interface those pretty easily. Other members in the ACT collaboration have done that. And I would suggest that if you have any specific question on that integration, to email the help desk, and we'll try to route those to the right people.
Great, thank you. Okay, this next one is for Matt. And the question is, are the Planck maps available in the ACT format?
The Planck maps are available in the ACT format, but not in the data release at the moment. So that's if that's something you'd like made available, we can look into that. So in order to combine our maps with Plonk, we did reproject it from Healpix to our pixelization, and we can look into making those publicly available. Thanks.
Great. Okay, the next question is for Zach. And the question is, can the notebooks be run on a laptop?
Yes, in fact, they are running right now on my laptop. So we made a lot of effort to ensure that the notebooks are as lean as possible. And so far we've had a good amount of success running on just standard home PCs without an issue.
Great, thank you. Okay, so the next question is for Simone, and it comes from Hideki Tanimura, and it is, does the ACT DR4 data include all the ACT poll data in 2013 and 2016? ACT MBAC is also included in the COAD map, ?
Yeah, so as far as the ACT DR4 is concerned, that's ACT poll data from 2013 through 2016, nighttime data. For the COAD map, it is correct. We also add the MBAC information in temperature from 2008 to 2010. So you will find that in the COAD maps. And of course, the old MBAC data is also available in Lambda separately.
Great, thank you. The next question is for Maya, and it comes from an anonymous attendee. Are the details of the co-edited maps and split maps discussed in the papers that were mentioned in the webinar?
Yeah, so the co-edited maps and the split maps, for the notebooks that use those maps, you'll see that we link to and cite the papers that discuss those. So if at any point you want more detail on the specific product used in a notebook, you should pretty easily be able to find the paper attached to it.
Great, thank you. The next question comes from Ichiro Komatsu, and it's for Matt. Do you also plan to make available the codes used to produce component-separated maps like the TSZ?
The code is publicly accessible, but it hasn't been advertised as such yet. But we do plan to do that. Yes.
Do you want to say what the code is called and roughly where you can?
So you can find it on the ACT collaboration GitHub, TILEC.
Great. Okay, this next question is for Simone. What simulations will be provided on NERSC, sorry?
Yes, so we do have Sky simulations that include basically the lens CMB simulations, and we provide code to make sure you can add foregrounds to that and being able to simulate the noise as Zach was mentioning. So we do release some byproducts for the noise, for example, the 2D covariances that Zach was mentioning, and then there is code that will allow you to simply generate as many simulations as you want. And then, of course, there is also simulations associated with the lensing maps and the component separation maps. And I should ask Matt, would you like to add anything since you have produced many of those?
No, that sounds good. Thanks.
Great. Well, let's see. Are there any more questions? And I should say that I'm not sure that the attendees are able to respond. But if you don't ask more questions in the Q&A thing, then we'll know that the answer is no. But obviously, if you have more questions, you should follow up by email to all of us. And then we are going to hold a summer school, or not summer school, depends on the season, but we'll hold a school to help people understand how to use these products in more detail, and just follow up with any of us or through the email that was mentioned earlier if you have questions. But with that, why don't we thank all the speakers, and we'll close this session. I guess it's sort of bad form for everyone to clap for themselves, so I'll clap for them. I don't know if the panelists are allowed to unmute. Great. Well, thank you, everyone.